Hey, what's up, YouTube? So today we are going to be taking a look at build systems. I thought it might be fun and cool to do a just kind of a gentle introduction to build systems. Just kind of a general overview of build systems, what they are, kind of like what they do, and uh, you know, uh, let's get into it. So build systems. What is a build system? So in general, a build system is a program that will take inputs. This is things like source code, libraries, assets, probably like other things that are, like other categories of things, and then turns those into executables or libraries. So I've got this, this diagram on the right. Generally, inputs will go into your build system. You'll execute the build system with these inputs, and then that will produce either a program that you can just run directly, or it will produce a library, which you can, goes into the set of inputs for some other build system run, and then that produces a program or another library. Um, so that's generally what they do. And in addition to that, like modern build systems will include um, stuff for like dependency management. So if you have like a JavaScript program that you're running or that you're working on, and you want to add like React, for example, then typically there's a way within the JavaScript like tooling that you can just to put it in your package.json, run a command, and then it will just it will make sure that you have React available to your code from that point on. This wasn't a thing for a while, like back in like the and even like C++ today. Like there's not a super easy way to just like say I want this package and then just like get it as part of a thing. There's stuff like Conan, and then like Bazel is also kind of trying to solve that, but it's not a super solved problem like it is in Rust and Elixir and stuff. Um, they'll also have like a bunch of task running. So that will include like tests, format commands and like linting and stuff. Um, those will all be part of like modern build tools, and then like other tooling that depends kind of on the system itself. And so just some examples like in C++ or C and C++, you'll have like make and CMake and Bazel. For Rust, you'll have Rust C, which is usually invoked via cargo. Elixir, you'll have you'll have Elixir C, which is usually invoked with mix. Like I don't know if I've ever like seen seen an Elixir C invocation like by itself. Um, JavaScript and TypeScript will have things like rollup, which is used in Vite, Webpack, and ESBuild, which are like not exactly build systems, but like they kind of do a similar job of taking your inputs and then like doing something with them so that they're ready for the browser or whatever. And then the truly cursed one is Excel, which is cursed knowledge that I will now burden all of you with. Um, and so what does that look like? So a build system is really more. Um, I guess there's kind of like two things that a build system does, right? So the main one is that it kind of like concerns itself with the dependencies of your task. In these two examples, like on the left, we have someone's writing like a hello world in C. They probably won't have any libraries or anything. They'll just have main.c, um, and that will produce a program that says hello world. And so that's pretty simple. It's your artifact is the program, and then your input is the main.c source file. Um, and then kind of similar. This is like not like a programming one exactly, but like profit, for example, is like a calculation that businesses will do, and roughly it depends on revenue and expenses. The exact calculation is not like really particular, or is not really like a consideration for the build system. The build system is mostly concerned with just like, okay, you need revenue and you need expenses. So if either of these change, then I have to rerun, part of the calculation that gives us profit. And similar to over here, like build systems for programming will also not really like care too much about how you put the pieces together. They're just concerned about making sure that the pieces are there, and like if they change, then then it knows that it has work to do again for the same program. Um, so what makes it difficult? It doesn't seem too hard. Well, it is pretty hard, as it turns out. Um, and the kind of the main reason is that dependency resolution, which again is like the main thing that a build system does. This is a very complicated graph problem. It is, in fact, I'm pretty sure it's NP complete, or it's NP hard at least. And what that basically means, if you're unfamiliar with like algorithmic with like complexity, is that it's going to take a long time to solve it if you wanted to solve it like completely. And so what most build systems will do is they will not solve it completely. They will make assumptions. They will impose constraints on their particular solution for the dependency resolution. And this is usually good, but isn't always perfect. And so like one thing that can happen, for example, this is an example. I don't know if it's like an actual example that would show up, but just for example's sake, this is a dependency graph of a some arbitrary cargo program or REST program that has dependencies of Warp and Tokio, and they have some overlapping dependencies. So for example, if Warp needs package A version 2, exactly version 2, but Tokyo needs package A version 3, and they need exactly those versions, then you can't unify the there's no like overlap between those two versions. And so Cargo can't say, okay, I'll just like for both of them, I'll just use this version. And so then what it does instead is it will either give up or it will build multiple versions. And so it will just take it will take version 2 and version 3 of package A, and then Warp will use version 2 and Tokyo will use version 3. And that may work, but also may have other problems. And so that's kind of where things can go terribly, horribly wrong. So why do we use build systems? Like, this is a difficult problem. Like, not all of them provide us with dependency management. So like, what else can they give us? Why do we use build systems over like a bash script or like a Windows batch file? That's kind of where the features of build systems come in. So, for example, one and also like not all build systems will have all of these features. These are like things that some programs don't care about being reproducible or being hermetic, and so they don't necessarily need these particular features. But for programs that do need them, then it's good to know how you get them. And so reproducibility is the feature of, given the same inputs, does the build system always produce the same artifact bit for bit? And so if I have a bunch of source code and libraries and assets, if I run it today with the build system, and then if I get the artifact and then I make a hash of that artifact, will I tomorrow, and for any arbitrary date, if I did it 10 years ago, if I do it 10 years in the future, then will all of those artifacts have the same hash guaranteed? And so that's what reproducibility is. So one thing that like kind of comes up a lot is like Docker builds. Like Docker does a lot of really really nice things. But one thing that is kind of confusing about them is that Docker builds are not reproducible just intrinsically. You have to do a lot of extra work, and I think I think it's still an imperfect solution, even if you do a bunch of like the mitigations for this. Partly because of like system time is kind of embedded into the layers in the metadata, which you can avoid that. But then kind of the other one is like if you don't have like really long running caches and you're doing a bunch of Docker builds, then like the apt-get apt-get commands are going to give you different timestamps of the packages that you get from from the apt repositories, and so reproducibility will then disappear, um, and that's bad. Maybe if you care about it. So then another handy feature that some build systems will enable is hermeticity or hermetic builds. And so that's kind of like given the same inputs and build system. If I run a build command on my machine with all of these inputs, and then I get an artifact. If I give you the exact same setup and have you run the same command, are you going to get the exact same artifact? And where this kind of like gets tricky is, for example, if we have like a C program, and I'm using, like we don't specify that we want a particular version of Clang or LLVM or whatever. And I say, or on my system, I happen to have Clang version 3.301. And then on your machine, you happen to have version 3.0.2. It is very possible that I will run the command and get a particular artifact, and you will run the command and get a different artifact by the hashes and bits and stuff. And so, it seems like a minor thing, but like this is very important for particular like domains. Like if you hermeticity is kind of like it goes into kind of auditability, and like software bill of materials and stuff like that, which are again not relevant to every program, but they are relevant to some programs. And so how do you get hermeticity? A lot of some build systems will do kind of like the sandbox approach. So they'll just they'll basically just like pull in like everything. Like they require you to declare everything pretty explicitly, and then they will just they will just download like those exact versions of everything, and then put them into a sandbox like in your local project. And so that's one way you can do it. Containers, Docker actually does help a lot with this. With like you can like kind of prepackage a container, and then like use that as like sort of the build environment. And if you like lock it down and make it like an air gap container, then like you can make sure that like building within the same container, you can use the container as like a build environment, and then more or less like get closer to hermetic builds. I don't know if that guarantees it, but that gets you closer. And then kind of the last one, which like it's kind of table stakes. Like pretty much every build system does this now. I don't know of any that don't. But incremental builds. Basically, if I have like A, B, C, like C depends on B depends on A. And then if A doesn't change but B does change, will the build system not like skip building A and then just build B and C? And as far as I know, like pretty much everything does this now. Like Make has been doing this for forever. So, and like Bazel will cache results. I think, again, I don't think I can't think of any build systems that don't do this. So it's kind of just just listed there as like, I don't know. Anyway, so then lastly, we've got just got kind of a few examples of like what a build system can do and like what invocations look like. And so the top left is like a basic, this is just like how do you build stuff. So this this first command is for make, and this will just make the default target of your make file. Cargo build, just build the application. npm run build. Again, so npm is kind of cheating because it's more of a task runner whenever it's with npm run. But I put it here because a lot of JavaScript development is like framework based, and a lot of the frameworks like their starter projects will all give you like a build command. So technicality, but it's there. And then Bazel has a build command. And then you also have to specify a target with Bazel. And so, in this case, like, we give it the target engine. And then bottom left is kind of like other things that the build systems can do these days. So like cargo also comes with like test and format commands that will, test your code and or run your unit tests, and then also like you can format your code in the cargo blessed kind of formatting. And then again, we have some cheaty npm examples. You can run test and you can run kind of whatever you want. But anyway, and then on the right here, please ignore the difference in colors. I forgot which one I used for these two, and then yeah. Anyway, so one thing that Bazel does, which is really nice, is it kind of allows you to it lets you do operations kind of like on or it lets you like investigate kind of the the graph that it produces for its build process. And so this is an example of like I want to get all of the dependencies of the engine target, and I want to get all of the dependencies, but only up to 2 deep. And then you can also have it output into a graph thing that will, with these other commands, you can then produce a PNG like this. And so, here you can see kind of like I've got the engine target as like the top level, like, this is the thing that I ultimately want to build with this command. It's got all of these dependencies of like, here's the source files that it directly depends on the here out to the right. And then it also depends on some other source files based on like the game target. And then the game target itself depends on the game headers target, which has a bunch of headers. And then we've also got a bunch of like third-party things. So like the SDL3 dependency is out over here. And then we've also got some of the like Bazel built-in stuff. So like the Bazel tools, which are kind of just like wrappers for the platforms thing. I'm not sure exactly what those are called, but yeah. So this is like just a nice example of like what these dependency graphs could look like in a semi-real project. Yeah, so that's pretty much all I've got. I'm going to put all of these links in the description, but basically these are just like further reading. Just some additional things that you might want to check out if you're interested in reading more about build systems kind of in general. So that's all I've got. Thanks for watching. If you enjoyed, please give this video a like. Please subscribe to the channel if you want to see more stuff like this. And if you have any questions, comments, or concerns, please leave them in the comments. So thanks. Hope you have a good day. And I'll see you next time.